be today talking about this upper left portion. So fossil fuels put CO2 into the atmosphere, and then we're kind of thinking about, okay, carbon is going to be moving around, and this is perturbing the carbon motion. It's kind of natural cycle when we're burning fossil fuels. And so then we'll come back to these other components that have to do with the energy budget next week. Okay, so backing up again, going back to our periodic table and remembering our kind of different components. So what is carbon? So again, carbon is this atom that is that has 6 protons in its nucleus. That is the definition. That is the name that we give an atom that has 6 protons in the nucleus is carbon. And we talked about that carbon is not necessarily the most abundant gas in the atmosphere. And it really only shows up in 2 different kinds of gases in the atmosphere. And that is carbon dioxide, which kind of in its name tells us what that molecule is made out of. So carbon, and then di means 2, and oxide means oxygen, right? So there's 2 oxygens. And then the other place the carbon shows up is in methane. And so methane is carbon as well, and then it has 4 hydrogen atoms. So it's not as its name is not as descriptive as carbon dioxide, which is, it could be called carbon quad hydrogen or something, and then that would be like equivalent to carbon dioxide. But instead it has this name, methane. And so these are, when we talk about carbon in the atmosphere, this is what we're referring to. We're talking about carbon dioxide and methane. And most of the time we're actually only just talking about carbon dioxide. But just know that that's kind of equivalent. We're talking about carbon in the atmosphere. It's not usually, it's in fact never just carbon by itself. It's carbon in this carbon dioxide molecule. So we care about carbon dioxide in the atmosphere, even though it's 0.041% of the atmosphere, particularly because of what we talked about last time, that carbon dioxide is a greenhouse gas. And so the other components of the atmosphere, nitrogen and oxygen, are not greenhouse gases. And so that's why we don't really talk about them in this class. But backing up even further, where did carbon come from in the first place? Carbon was formed in the core of giant stars. So our solar system is what's called a second generation solar system. That means that there used to be a star, and it was, what stars do essentially is they fuse hydrogen atoms into helium atoms, and then they'll eventually fuse helium atoms into heavier atoms. You just think about like how many, what these numbers are, proteins in the nucleus, or not proteins, protons in the nucleus. And if you have a star with a bunch of gravity, you can kind of smash a bunch of protons together and form atoms with more protons in the nucleus. So you need a star like that. You need a really big star in order to form these heavier elements. And so carbon, like all of the heavier elements, was formed in stars. And then eventually the stars at the end of their life, they explode and they project all of their materials into space. This isn't really part of the carbon cycle. It's just kind of a fun fact to think about. And so then our solar system kind of condensed and coalesced out of that cloud of dust that had heavier elements like carbon in it. And so that's why there's carbon to begin with on Earth. And so where is carbon on Earth? Well, it's in lots of places. So we think about carbon a lot in terms of this class, in terms of fossil fuels. So if you're thinking about like a coal burning power plant, there's going to be carbon in the coal. And then what's coming out here, what you can see is actually like water vapor. But there's carbon dioxide coming out of those smokestacks as well. So that's kind of an obvious place where carbon is now. There's carbon in things like, okay, diamonds are pure carbon. So that's one place where we see carbon. There's carbon in our pencils. So graphite is essentially carbon. And how about this? Where is the carbon in this Coke bottle? So there's carbon, yeah, so this is like a big picture of carbon. So plastic is a petroleum product. So plastic is made out of essentially oil, and so it's made out of, there's carbon in the material. And then the corn syrup is sugar, which has carbon in it. And then it's a carbonated beverage, which just means that it has dissolved CO2 in the liquid. So when you undo that cap there, it releases that CO2 in the form of bubbles to the atmosphere. So that, going along with that sugar theme, there's carbon in this dish of pasta, right? And what's an easy way to remember that? What do we call this? Yeah, carbohydrates. And so that's referring to the carbon in them. Say we're going to have a big plate of carbs. And so that's same thing with the ice cream cone, carbohydrates. And in addition to carbohydrates, our kind of other nutrients are fats and proteins, but those are also hydrocarbons. They're just kind of, the molecules are in different configuration, but fats and proteins are definitely have carbon as well. And we see carbon all over the earth. So as we've kind of been talking about, this material here is going to be carbon because it's organic life. And then this happens to be a picture of limestone, which is calcium carbonate. And so there's a lot of carbon in rocks. The point here is that carbon is all over the place. And finally, carbon is in us, because we are life forms, we are organic matter, and that is essentially, so like, I don't know if anyone in here has taken OChem, and OChem stands for what? Organic chemistry. So organic chemistry means the chemistry of life, right? And then the chemistry of life is essentially the chemistry of carbon. So carbon, we call ourselves, yeah, carbon-based life. And so life relies on carbon. And it's 18% of the human body by mass. And so that means if you were just doing the calculation, if you're 165 pounds and you're carrying around 30 pounds of carbon. So it's definitely not a situation that it's like carbon is bad or something like that. Carbon is an intrinsic part of life, and it actually helps keep the climate hospitable for life as well. But moving a bunch of carbon from underground to the atmosphere, as we will see, essentially is bad. But okay, so carbon is created in these huge stars, but on Earth, is it created or destroyed? And the answer to that is no. And that's really helpful scientifically. When we can say something is not created or destroyed, we can call it conserved. And that means we can just track it as it's moved around the Earth system. So we don't need to worry about like, oh, is it created here and destroyed here? And then we don't really know where this came from because something could be created. It's actually a lot easier than that. You just kind of track where it is. And so that's kind of what the whole idea of the carbon cycle is you're just tracking carbon as it's moving around the Earth system. So the point of that introduction is just that carbon is all over the place. and that it's not created or destroyed. And so now we're going to talk about exactly how it moves around the system. Okay, so going back to my diagram, what I've taken out of here is the shortwave and longwave radiation from the sun and the clouds and all the different greenhouse gases. And we're just going to focus on the carbon moving around in the system. And so I'm going to be showing you some different measures of carbon. So the way that it's measured is in gigatons when we're talking about the whole Earth. And so you'll see this abbreviation. So you get gigaton and then gigaton of carbon. GTC is our main measure of the mass, the amount of carbon in various places. And so on this diagram, I'm going to be showing you reservoirs of carbon, which means, and those are all in white, and a reservoir is just how much carbon is in this location. And so we can start putting those on here. So by far the most carbon on Earth is in the Earth's crust. So this has 50 million gigatons of carbon in the Earth's crust. So I showed you limestone was calcium carbonate. There's carbon in that. And there's carbon in a lot of different rocks. And so that's where most carbon is in rocks. Then there's a lot of carbon, but much less in the ocean. You will not need to know any of these numbers, just kind of to give you a rough sense of where the carbon is. There's 10,000 gigatons of carbon in fossil fuels. You'll see actually kind of wildly different estimates of how much carbon is available in fossil fuels. And a lot of that has to do with estimating, how much would actually be extractable, and then is it just, physically extractable or economically extractable, as in like, could you actually, practically get at it, that type of thing. And so this is kind of on the higher end of the estimate, but end of the estimates, but this is roughly how much is in fossil fuels, 10,000 gigatons of carbon. There's much less in the soil, 2,300 gigatons of carbon in the soil. Soil is organic, kind of, mostly dead and decaying organic material, so it's going to have carbon in it. 1,700 gigatons of carbon in permafrost. Permafrost means soil that is more or less permanently frozen. So that's, again, has carbon in it for kind of the same reason the soil does. It's organic material. And then 800 gigatons in the atmosphere. So we're getting to less and less amounts here. So 800 gigatons in the atmosphere. And then our last value on here is how much is in plant biomass on the surface of the planet, 550 gigatons. So I just went through those in order from most to least. So we have the most carbon in the rocks on the Earth's, in the Earth's crust, and the least carbon of these reservoirs anyway in the terrestrial biosphere, or in plant, just the plant matter on the surface of the planet. So that's kind of where it is. And then we're talking about the carbon cycle. So we want to know, how is it moving as well? And so I'm going to put on here some arrows in black. And what the black arrows are is they're flows of carbon from one reservoir to another. And they just mean how much carbon moves from one reservoir to another, and it's over the course of a year. So that's important, that it has a unit of gigatons of carbon per year. So our most important flows, we touched on this a couple times so far, have to do with our photosynthesis and respiration equations or relationships. And so what is, let's see, sorry. Okay, so what is a good way to remember our photosynthesis and respiration equations and relationships here? Well, I think the easiest way to do that is to start with just asking yourself the question of what do plants need to survive? So there's at least 3 things that are really relevant here. You know, there's probably 4 or 5. I mean, you could come up with a lot more, but so what do plants need to survive? But so these 3 are what that like tells you what everything you need to know to begin with, to know what the photosynthesis and respiration equations are. And so this brings us to another question of why don't you need to feed plants? Why don't you have to give it a mouse or something like that? They make their own food. Yeah, they're called autotrophs or primary producers. And yeah, they're making their own food essentially out of the energy from sunlight. So that is what is being shown in our photosynthesis equation. Their plants need CO2 from the atmosphere, so that's here. They need water, H2O, that's here. They're getting that from the soil. And they need sunlight, that's here, that's their energy source. And they are using that, and remember, we are conserving all of our molecules. We're not creating or we're conserving all our atoms. We're not creating or destroying atoms. So anything that's on this left side of the equation has to show up on this right side as well. So we have 6 carbons over here, and then they show up over here as 6 carbons as well. But what the plant has done is it's rearranged the atoms in a different way, where it creates this sugar molecule, glucose, that is stored in the plant tissue. The plant releases oxygen to the atmosphere. So it was, we call this oxygen when it's diatomic oxygen, when it's just pure O2. But those oxygen molecules before were part of CO2 and part of water, part of H2O. But it releases that as oxygen to the atmosphere. And it's storing this energy in the bonds of the sugar molecule, which it can then use for its own metabolism, and then other things can eat for their metabolisms. But what this whole equation represents is you're taking CO2 from the atmosphere and you are storing that carbon in the plant tissue. So going to our diagram, that means that photosynthesis is taking carbon out of the atmosphere and putting it into plants. So it's not necessarily, you'll see this kind of that it's like CO2 goes into the plants, and that's not technically correct because the CO2 itself is not being stored in the plants. It's really just the carbon component, which is in this sugar molecule that gets stored in the plants. But so photosynthesis, the important point, photosynthesis takes carbon out of the atmosphere, stores it in the material of the plant. And then respiration is just the opposite of this relationship. So in respiration, you start with what's over here. So this is now the respiration side. So we're starting with the sugar that's stored in the plants, and so plants respire, or animals that are eating the plants respire. They take in oxygen from the atmosphere, they combine it with the sugar from the plant, and they use they use this to produce energy. It's essentially like they're releasing the energy that came from the sun that's then they're using that energy to run their metabolisms. So that is what I am doing right now. When I'm moving my hands around, I am breathing in oxygen from the atmosphere, and I am using sugar that's in my body that I ate recently, right? So I either ate a plant or I ate meat that essentially is plant material that was converted into a fat or a protein. I'm breathing in the oxygen from the atmosphere, and I am getting energy out of that to run my body and to move my limbs. So I'm in this way, you can see that I am solar powered because the energy originally came from the sun. And what do I do? I breathe out CO2. Keep in mind, respiration, we talk about breathing. That is respiration. It's the same thing. So I'm breathing in the oxygen, I'm breathing out CO2, I'm breathing out water. So that means that since the CO2 is now, or since I'm producing CO2 when I'm breathing, and that carbon came from the sugar molecule, that is going to be now a flux back into the atmosphere, or a flow. Flux is the same thing as a flow, a movement of carbon back into the atmosphere. And so these, prior to the Industrial Revolution, more or less balanced out, where you had just as much carbon going into plant material every single year as was coming back out every single year through respiration. So photosynthesis takes it in, respiration puts it back, and so the ecosystems on net, so animals that were respiring, were putting back as much carbon as was coming in the first place. And so the last thing I'll mention here, this is your fourth question on the discussion questions, is I want to bring up the relationship that this respiration equation is so central to so many of the different things that we're talking about. And the details differ a little bit, but when we talk about like forest fires causing carbon emissions, and when we talk about burning fossil fuels causing carbon emissions, and what I just talked about with myself breathing and breathing out CO2, those are all essentially part of this same type of equation. So burning forest fires, working out burning calories, or burning fossil fuels are all doing something very similar to this. They are taking carbon that was in organic material, taking oxygen from the atmosphere, producing energy. You can see energy here, right? There's a bunch of energy coming out of this forest fire. This is producing energy to run our cities. This person is burning calories to produce energy. So we are getting energy from the molecules of the organic material in all of those cases. And so I want, my fourth question on the discussion questions is, if you have a scale in your house, like a weight scale, I want you tonight before you go to bed to weigh yourself. And it's not important that you're sleeping or whatever. It's just it's important that a unit of time has passed, a certain amount of time has passed. And then I want you, the first thing when you wake up, after 6 or 8 hours or whatever, to weigh yourself again before you go to the bathroom. And I want you to tell me if you lost weight. And you should lose weight because you should be breathing all night and converting some of this material in your body into carbon dioxide that you're breathing out and to water that you're breathing out. And if you don't have a scale, you can just say, I don't have a scale, or you can lie to me and say that you lost weight. Either way, I just want you to do that. But I think it's a really interesting and important experiment. because it, you know, brings together like a lot of themes in science. You have conservation of mass. You can't just lose weight without it going somewhere. It has to go somewhere.